In this video, we're going to take the Pyro sim that we've been building, and we've just modified the rigid body explosion by adding some softness to it and a better way of transferring the velocities over. And I've just cached up the collisions. As you can see here, I'm just loading in the cache, ready for my Pyro sim. So what I want to do with the Pyro simulation is to, now that I can go inside DOPS, is to go inside and add some custom solvers to fine-tune the look. So let's have a look at how we can do that. So I'm going to select this first, and I'm going to go to the Shape tab here. I'm going to make sure we're going to use minimal OpenCL. And I'm going to go to the Shape tab here. I'm just going to turn off the disturbance, shredding, and turbulence for the minute. And let's just increase the resolution here, maybe to 0.15, just for a bit of speed. So if I play through now, you'll see we're not going to get any of the detail. We're going to see those smooth, sort of mushroomy, cloudy, looky type bits on there. Yeah, there we go. We can see that nice roundness, the roundness that we're trying to avoid by adding all these noises in. So the one limitation about this, for example, is you can only add one layer of noise. You know, things like the disturbance, the different methods there look quite nice, and in combination they can work really well together. I'll show you what I mean. I'm going to go inside that DOP network. So that if we go inside the Pyro solver here, so again, like we saw with the rigid bodies, we can add in sort of forces here, but this time, unlike the rigid bodies where we're dealing with geometry and points, in here we're dealing with volumes and fields and other bits and pieces. So in here we can wire in the gas microsolvers. If you hit tab and type gas, these are all the kind of nodes that you can use, and there's quite a few complicated ones. Now the one I want to use actually is the disturbance. Let's actually let's have a look at gas wind first. So let's type wind. So like we did with the rigid bodies, we can add a simple wind force. So let's plug that in. And similar to the particles, you'll see we've got wind direction and scale, but we'd have to add noise in separately. And you'll notice there's a time scale here. So again, that needs to be similar to the time scale on your sim. So if you come up to the simulation tab here, you'll see the time scale. What I'm actually going to do is right click and copy parameter so I can link up everything inside. And it's a good idea to have the time scales all matching. So let me paste relative reference here, but it was 0.75 if I need to remember it. So let's put a bit of a wind scale in there, and let's press play, and let's see what happens. And instantly you see it starting to blow sideways. Now there's a slight issue with this. Now not all of these nodes will accelerate on OpenCL. Some of them will have a button you have to select. So sometimes when you add them in here, you'll notice with the minimal solve it will just go really slow. So you can't use them with the minimal solve. That means you can still use them with the sparse and the dense solve, but just not the minimal. So if I just pop up one, we'll see that the shading kick in. Oh, it didn't kick in. That's nice. So yeah, let's press play again, and then we'll see it happen at this level. And we'll see the winds blowing it across. So you can add lots of custom forces, wind forces and other bits and pieces directly inside there. Now we're not going to use that one for the moment. I can always turn it on a bit later. So we'll add a merge node. And this is DOPS, so again, the order that we add things into the merge node is important. It's the order that things will happen in. So the one I want to look at now is gas disturbance. So let's, oh, there we go. Let me type that in again. Gas disturbance. There it is, gas disturb. Let's plug that in. And you'll see it's pretty much the same as the one above, because it is the same as the one above. The difference is I'm going to add lots of bunch of noises here together. So the first method I'm going to look at again is this continuous method. I quite like this one. So let's put 35 in there for a bit more strength. And let's have a look and see how that looks. So let me press play. And we'll let that run through. And remember, we'll see the disturbance breaking up those sort of mushroom clouds. Now this one just gives you that really nice small scale noise. It's good for small scale noises. Oh, I should have gone up one to preview this, actually. So is the graphics card going to like that? Not so bad. There we go. It's because we haven't got a nice spotlight on there. Let me stop for a sec. It's because we don't have our nice spotlight on there. We've got I turn this headlight on, so it's looking a bit funny. There we go. Let me stop it. If I put the high quality lighting on, we've got the. Let me turn the grid off. We've got the IBL in there. I suppose we can see some nice detail going on, and it is quite soft. What I'll do is just come up the top level, and I'll turn off the display of the environment light in the background here. So if we select the environment light, let's turn off enable light in viewport. just so it looks a bit better there. So where were we? We're inside the house model node. And oh yeah, now we can't see the environment light on that. That's handy. So what I might do is just turn on my spotlight reference here. My reference spotlight, because that was nice illumination before. So I'll turn it on with that. That way we'll be able to see it. There we go, nicely lit in here. We can see that detail. So you can see what the let me click the pin icon here up the top. That'll keep this interface at this level, so I can dive inside and still see the nice shading. So this is what's creating that high frequency detail here, based on the strength. So it's a really nice feature, but it's not going that quick, as you notice. If we actually click on here and turn on Use OpenCL, you'll notice it'll go a lot faster. There we go. So because now it's able to use the minimal solve. So you must look in some of these nodes that it has that button on it. As you saw in the gas wind, it didn't, but it was still quicker. So there we go. We're coming through, and we can see how this disturbance, this continuous noise, which is quite nice. So let me just disable that. This rotational force can be quite nice to turn on as well. Oh, actually, let me paste relative references to make sure the timescales are the same. Yep, there we go. So make sure that says 0.75. So yeah, the rotational force is quite nice. You know, as we're applying force to these vectors, the force we're applying is trying to aim to a common axis. So it gives an overall sense of swirliness to it. So that can be quite nice to turn on sometimes. And you'll see as it evolves, we get these small scale features appearing on those smooth sort of mushroomy bits we were seeing. So this is good for that small detail. What I like to do is add several of these at different types of noise, just to add that complexity. So I'm just going to disable that for a minute, and just to remind you how it looks, we'll just zip forwards a few frames. It's a little quicker if it doesn't have to update the display. And look, you'll see we're losing all that high frequency crunchy detail there. So let's make another gas disturbance. And in this one, oh, where did it go? There we go. So in this one, I'm going to actually use the block-based method, because this will give me control over the size of the swirls. So let's stick this to 30. And yep, let's also have some rotational force, and let's paste relative reference in the time scale to make sure that's linked together. And again, the advanced tab, we should turn on OpenCL. That's quite important. So I'm going to make the block size quite big. I want to break up those mushroom clouds with quite big noise on top. So what I might do is just decrease the resolution a little bit so we can see a bit more of the detail there. Let's maybe put this to 0.12. And let's jump forward a few frames. So remember, it was that kind of blobby look, but now we've broken that up with this kind of bigger, larger scale noise. So let's jump forwards a bit more. There we go. We're getting these sort of larger structures breaking up that mushroomy look. And what we can do is, what I'll do is I might just flip book that up with a slightly higher res. Let's put that to 0.1. So I'm just going to right click and run a flipbook and just see how that looks at this quality. And then I'll pause the video and we'll come back and think about how it looks and decide what to do next. Right, that's flipbooked up. So if I press play, we can see that's looking quite nice. We've got those big structures from that noise. What I might do now, and actually I can see it's still evolving all the way to the end. So what I might do now is just turn on the control field like we discussed in the earlier videos, and I'm going to link that to the speed field. Which one's this? Oh yeah, that's the block size. So let's go to the control. Let's just remap it with a linear. Make a big number here. So it will start off with a lot of noise and then soften up quite a way into the simulation. Let me see if I can just jump forwards a few frames and see if we can wait to see that. So there we go. So again, if we go towards the end here, whereas before we saw all that swirling noise, you'll see it fades off quite a bit and looks a lot smoother, as it does, because as the smoke goes in the air it kind of diffuses more. And as soon as we get later here, we're not seeing all that constant swirling, because it's faded off with the time there. So what I'm going to do now is add a bit more detail by bringing in this continuous one. So again, if we jump forwards, we had those big nice structures which we softened a little bit with the gas disturbs control field. Now this continuous one is going to add, you see there's sort of high frequency noise on top of all those big bobbly bits, so that's looking much more interesting now. So this one's creating the big structures, this one's creating the noise on top of that, and again you could put another layer to create maybe another mid-level of structure in between. So look, we're getting these big fluffy balls and we're getting this high frequency noise over everything. That's looking much better. And you can get a bit more subtle control over this stuff. For example, if you add a gas blur, there we go, gas blur, let's put that at the end. So what I'm doing is I'm applying the continuous first. Actually, we should swap these around. So in the merge, I can just swap these two arrows around. And there we go. So we're applying the big noise first, then we're applying the crunchy little stuff on top. And now we can apply a blur. So again, here's the time scale. Let's paste relative reference so it's locked. And again, turn on OpenCL. So let's put a bit of a large blur in there, and you'll see what it does. So again, if I run forwards, so if you get any artifacts, you can apply a blur here and just help soften it out. But generally, upping the resolution is what helps there. So that already that's looking. Is that looking softer? Might need to make that a bit more extreme to see what that's doing. Don't want to blur it too much. Let's try that a bit higher. Oh, hang on. No wonder it's not having an effect. I haven't told it what field to use. So up here, when you apply these nodes, you must tell it which field to apply to. So we're going to blur the density field here. Okay, so we're going to blur the smoke essentially. So yeah, a radius of 2 again. Now we should see an effect. Deary dear. Must remember to do that. So yeah, when it says field, you've got to tell it which field, obviously, that you want things to happen in. And look, there we go. We've totally blurred up the density there. So if we, let me just stop that. So you can use this maybe over time. If you want to animate it over time, you have to change this use default to set always. Otherwise, it only sets it on the first frame. So if you set this to set always, you can then keyframe this over time. So look, we've softened it up quite a bit. Let's have maybe a tiny bit of softening, like 0.02. So that, you know, you can control how the gas kind of blurs up as it dissipates and stuff. So we've added a little bit of softening there, which might remove some of the artifacts at being low res, but obviously upping the res will help a lot here. So just blur it really subtly there. Blur the density field if we want to. So there you go, that's added a lot of detail for us using these Microsolvers. So there's one last little trick I want to show you actually. You can go a little bit more advanced than that. Let me just turn these off. So what we can do is we can create our own custom fields to do stuff. So first of all, let's create a gas match field. This will create our own field within the sim to work with. So I'm going to create a field based on height, and I'm going to use that to affect the buoyancy here, just for a bit of fun, just to show you the kind of stuff you can do and how customizable this stuff is. So the gas match field, we want to create a new field here called, let's call it height, and we want a reference field there. And the reference field is the field it's going to copy, basically. So we want a copy of the density. So it's going to copy the density field and call it height for us. And since the density is a scalar here, you must get the data type right. So that's just created an empty field with no data in it. So we need to populate some data in it. So for that, I'm going to use a gas field VOP. So there we go, a gas field VOP. So this is allowing us to use good old VOPs to manipulate the volumes. So if we go inside, it's pretty much like a volume VOP. And the nice thing about this is, if you look actually up here, it says in the bindings, auto bind by name, which is pretty handy. It means you can literally bring in a bind node. And we created a scalar, which is a float field called height. So if we do this, it'll bind it by name and actually bring in that height field data. I don't want to do that. I don't want to bring it in because it's empty. What I want to do is create some data. So I'm going to use a relative bounding box. So relative to bounding box, And we're going to plug in the first input here, so it's our volume, it's our geometry, and our position, and this will give us a vector 0 to 1 based on the y height. Because we're using OpenCL, it's a fixed box. Obviously, if you're using your own box, you don't know the ranges. So what we'll do is we'll do a vector to float, so we can access the y component of the bounding box. Now I'm going to stick that through a fit range because it might change. So we're going to get here a 0 to 1 value based on the bounding box. It's probably actually better if I just plug height straight in directly, because the bounding box could potentially change later on. We won't use relative bounding box because that 0 to 1 range is going to change as the box grows. Whereas if we use the position in world space height, that will depend on the world space height. So yeah, we can use a fit range instead. Fit range here, so to put our y height into sensible values. So we'll plug the y, or the value 2 here, into the value. And here's our source minimum maximum. So we know the y height's probably 0. So we'll promote the maximum here. We'll call this height. And what this will do, let's call that height as well. So what this will do, it'll remap that range 0 to 1. So if we've got a 0 to 1 range, we can put that through a ramp parameter. So a ramp parameter, there we go. And I don't want this to be a color ramp, I want it to be a spline ramp. And we'll use this as our height field data. So at the 0 in y, we'll get 0, and at the top of the y, at this moment, that'll be 1. So at 1 in y, we'll get the full value. And we'll use this as sort of a multiplier for a field there, as a controlling field. So you can make masks and controlling fields like this and use them in these sort of ways by creating your own custom fields, and I'll show you how you can mix them in to other fields. So we can use a bind export, because again it's using that name thing. So if we just plug this in, and we want to call this height and make sure it's scalar, and that will write into our new field that we created there. So now we've populated that field with some data. That's the important thing. So the next thing we want to do is do something with that data. So there's plenty of ways that we can do this. So I'm going to simply just add some buoyancy. So we'll do some gas buoyancy. So gas buoyancy, hitting the wrong keys there. There it is, gas buoyancy. Let's plug that in at the end. So here we're creating that. Remember, the order is important. So this is creating the field first, from copying the density field, and it's empty. Here we're filling that field with values 0 to 1 based on the height. At the moment that's 0 actually. Oh no, where's the height? It's oh, there's my ramp. Let's put the ramp up here. And where's my parameter value that I promoted? Gas field VOP. Where are we? I thought we promoted that up to, oh, it's called height as well. Max, we'll call that height max. Has to have a unique name, otherwise the attributes clash, and then things like that happen, they don't appear. So if I come up one now, there's my height max. So what was the height actually? If we go to the setup, it's about 31 units. So actually, let's not do it in the y height, let's do it across the x-axis. That might be more fun. Then we might see a bit more of a result of what's going on there. So yeah, let's actually go back inside the gas field VOP. Instead of the y, let's do it across the x-axis. There we go, let's rotate that around. So across the x-axis here. So we'll see the effect in half the box potentially, which will be what we want to do. So in the gas buoyancy here, at the moment it's using the temperature field as a kind of a multiplier. It's giving it a buoyancy lift, and then that's adding here to the velocity. Remember to turn on OpenCL and connect this to your timescale. So what I'm going to do is actually give it a negative buoyancy, like -500. So it's really cold, it's going to push it right down. And we're not going to use this temperature field, we're going to use our custom height field. So where our height field is 0, then we'll get 0, and then when it's strong we'll get a lot of an effect there. So let's make this more obvious. I'm going to select the field VOP here, and what we'll do is we'll just move this to the center, and we'll make this a constant interpolation. There we go, we'll move that to the center. So it literally just switches halfway through. And let's make the height maybe something like 10 units across. Actually that's going from 0 to 10, isn't it? So yeah, we need to go from -10 to +10 if we're doing it across the X, because remember we're centered to the origin there. So what I really want to do actually is let's promote this one, and we'll call this height min. Let me spell that correctly. There you go, again having to have a unique name for that parameter. So here, oh, went too far. So there's my height min, so let's do -10, because it was, is that right? What was the size? 15. Okay, 7.5 either way. So minus, oh that's plus 7.5, 7.5, minus 7.5, there we go. So hopefully at the midway point, we're going to get buoyancy pushing all the way down, and then we're not going to get any, we're going to get zero buoyancy elsewhere. So let's press play and see if that works. So you can see it's already pushing it down. Now it's adding it into the equation. We're pushing those velocities down, but then, you know, they've got to go somewhere. So we're getting these really strong eddy currents going around there. So maybe if I increase the range, let's have that actually go from 0 up to, was it 7.5, isn't it? So if we do this here, and it's not quite at the center, it's like halfway through the halfway point, and let's maybe not make it so strong there. So in the gas buoyancy, let's make it 100. But the important thing is, you can see here, I'm sort of manipulating, I'm creating fields and data, and I'm adding that into the equation with my own sort of custom fields here. And you can do whatever you want really, obviously you can customize it loads. So that we've got a downdraft here where it's cooling it loads, or it's got a minus buoyancy, so it's forcing a negative velocity down that way, which is forcing the smoke across the bottom boundary and up and around. And you're getting those sort of crazy eddy currents there. That's not really kind of the effect I want in this, but I just wanted to demonstrate that, sort of how you can build your own custom fields. So let me just turn those off. I do want these on by the way, so let's turn back these noises on. So my disturbance at this layer, at this level, with the block base give me the big structures, then the continuous give me the fine little structures, and then we've got the blur, just blurring everything up a little bit. And what I'm going to do, come back up here, and I'm going to turn on, back in my shape here, the shredding and the turbulence, because those other guys made it look quite good. So now you've seen a little bit of how you can sort of dive in there and customize your Pyro solver to get it to do what you want. And notice how things were quick because I used the minimal OpenCL solve, and I tried to use the nodes that supported that. Obviously if you don't, you'll just have to flip book it and just wait and have patience to see it properly. So the last thing I want to do now actually is turn off the minimal OpenCL solve, and I'm going to go to the, where is it, the setup tab, and we'll put back our low res 0.05 like we did before, and I'm now going to cache this out. We'll call this version 2, so we've got the higher res simulation there. So yep, we've got the sparse solving. Just check that. Yep, I've got the sparse solving on. So everything should all work the same hopefully and look similar. So I'm just going to stop the video now, and I'm going to cache that out. And once I've cached that out, I will render it up using the same settings as we had before, and then I'll stop the video obviously for that, because that's going to take a little while, and then we'll come back and just have a look at that video. And then once we've had a look at the final render, we will then look at how we can import all of this data that we've created into Solaris, into the USD format, and then we'll look at rendering it in Karma. So let me just pause the video now while I render this up with the cache this out with the correct collisions. Oh, that's why it's previewing slowly, because I had the collisions in there. So yeah, let's cache this up with the correct collisions in there now, and I'll see you in a moment when it's all finally rendered. There we go, this is finally rendered, and let me just play that. So that was the new cache with our adjustments in there and our added Microsolvers, and rendered through the same mantra settings as before. And I'm quite liking that. I'm liking sort of the noise. We can see the big shapes and the high frequency noise we put in there. And we could work into this a bit further, make it a bit more crunchy if we wanted. Maybe change the shading. But I'm very pleased with that result at the moment. So what I'd like to do now is take this scene and prepare it for Solaris. and that means we're going to convert stuff to USD and then load it into Solaris and render it through Karma. So let's do that in the next video.